In this session, we're going to solve more exponential and logarithmic equations. We are going to solve them with exact answers and approximate answers accurate to 4 decimal places when we need to use a calculator. First up, 5 to the x is equal to 3. Now because the base is 5 and we have a variable in the exponent, we can use a base 5 logarithm. And that would look like this. Log base 5 of 5 to the x is equal to log base 5 of 3. You see, we can apply the logarithm to both sides of the equation. On the left-hand side, since we're looking at log base 5 of 5 to the x, we have that cancellation property that would give us that x is equal to the log base 5 of 3. But now, while this is an exact answer, this is not useful for a calculator. I'll say it's not calculator friendly. But by using the change of base formula, we can say that this is, for instance, x equals the natural log of 3 divided by the natural log of 5, and that is a calculator-friendly exact answer. There's an alternative way we could go about doing this, though. Recognizing that I want a calculator answer at the beginning, what I could do is apply, say, a natural logarithm or a common logarithm to both sides, and use a property of logarithms. And so, starting out with the same equation, I'm going to hit both sides with the natural log. So I have the natural log of 5 to the x is equal to the natural log of 3, and as before, we're changing both sides in the same way. There's nothing magical about the natural log. I could have used the base 10 log. I can use a base 27 log, it's just not to our advantage right now. In any case, on the left-hand side, where we have the natural log of 5 to the x, exponents come out front of a logarithmic expression. You see, that's the property of logarithms. And so we would write down x times the natural log of 5 is equal to the natural log of 3. And now what I have is just a linear equation because the natural log of 5 is a number, the natural log of 3 is a number. And since on the left-hand side it's being multiplied, x times the natural log of 5, what I can do is divide by the natural log of 5. And get that after reducing, x is equal to the natural log of 3 divided by the natural log of 5. You see, it's the same calculator-friendly answer that we got. We're going to end up using this technique of applying either a natural log or a common log to both sides. Usually I'm going to use the natural log because I prefer to write ln. Now we were also asked to give a decimal approximation accurate to 4 decimal places, and so I'm going to say that this is approximately, and then I'm going to get an answer out of my calculator, and it's telling me it's approximately 0.6826. Now I know this is a little bit weird, it takes some getting used to. The expression natural log of 3 divided by natural log of 5 is actually the exact answer. Just like, for instance, the square root of 2 is an exact number. The decimal answer, 0.6826, is an approximate answer. Just like the square root of 2 is approximately 1.414. Okay, so the one with the decimal point is usually going to be an approximate. The one where it's natural log that you don't like to look at, that's the exact answer. I'm going to want to see both. For the next equation, we're going to use the natural log, and we're going to use the property of exponents that we just saw. We have 3 to the 4x plus 5 is equal to 8 to the x minus 1. So the first thing I'm going to do is apply the natural log to both sides of the equation. And a log is how you get a variable out of an exponent. So I now have the natural log of 3 to the 4x plus 5 is equal to the natural log of 8 to the x minus 1. At this point, it'd be useful to note that the exponents in both cases are binomials. And so when they come out front using that property of exponents, we should use parentheses. That's a common mistake. People don't use parentheses, they don't distribute where they're supposed to. You'll see what I mean in just a minute. But let's write down what happens when the exponents become coefficients. So just as before, with the exponents coming out front, I now have the binomial 4x plus 5 quantity times the natural log of 3 is equal to the quantity of x minus 1 times the natural log of 8. Now I have a binomial times a number, the natural log of 3. So I'm going to distribute the natural log of 3, because one of the strategies that I have when I'm dealing with an equation is I like to clear parentheses. And on the right-hand side, I'm going to distribute the natural log of 8. What this is going to look like is 4x times the natural log of 3 plus 5 times the natural log of 3. So that's what it looks like to distribute the natural log of 3 on the left-hand side. On the right-hand side, we have x times the natural log of 8 minus 1, if you like, times the natural log of 8. Now we got to keep in mind what we're solving for. We're solving for x. So what I'd like to do is get all of the occurrences of x on the same side, and then I can factor and then divide. Because I have terms with pluses and minuses running around, we're going to add and subtract as appropriate, actually in this case just subtract, to get things on the same side. That is to say, if I want the 4x times the natural log of 3 and the x times the natural log of 8 to be on the same side, then I'm going to subtract one or the other to bring them together. First, let me erase those underlinings because I didn't want it to unduly look like a fraction. And I'm going to subtract x times the natural log of 8 from both sides. Now, I don't have anything like terms on the left-hand side. On the right-hand side, the x natural log of 8 goes away. But on the left-hand side, I have to write everything out. So I have 4x times the natural log of 3 minus x times the natural log of 8. That's what it looks like to subtract those two when they're not like terms. Plus 5 times the natural log of 3, because nothing has happened to affect that one, is equal to negative natural log of 8. You see that was a negative term. It should still be a negative term. Well, I've gotten partway through what I wanted. I wanted to get the x's on the same side. Now what I want to do is get everything that's not an x and put it on the other side. And what that means for me is I'm going to subtract 5 times the natural log of 3 from both sides. Again, recognizing that I don't have like terms. So we have 4x times the natural log of 3 minus x times the natural log of 8 is equal to the negative natural log of 8 minus 5 times the natural log of 3. So this is like solving a linear equation in beginning algebra. We're subtracting terms to move them from one side to the other, with the goal of getting the x's all together. And the reason that we want to do that is because now we can factor the x out of the left-hand side, you see. And when I factor it, I have x times the quantity of 4 times the natural log of 3 minus the natural log of 8 is equal to negative natural log of 8 minus 5 times the natural log of 3. In other words, I have x times the parenthetic quantity, and so if I actually divide both sides by that parenthetic quantity, I'm going to end up isolating x. So I'm going to divide both sides by 4 times the natural log of 3 minus the natural log of 8. And on the left-hand side, that factor divides out. I end up with x all by itself, which is what we were after this whole time anyway. On the right-hand side, doesn't really look pretty. Negative natural log of 8 minus 5 times the natural log of 3 divided by 4 times the natural log of 3 minus the natural log of 8. That is the exact answer. My calculator tells me that this is approximately negative 3.2710, and because I'm not writing down all of the digits, it is actually an approximation, and I'm again going to want to see both of these. Some people will at an earlier stage start putting things into their calculator, and they'll start writing down a bunch of decimal answers. And then they have to write, number one, they have to write a bunch of decimals throughout the rest of the problem. And number two, they lose the ability to actually write the exact answer. I don't want you to do that. Don't put it into the calculator until the very end. You might want to write that down. Next, we have a logarithmic equation. And I know this because I have a variable inside of a log. And what it is the log base 6 of the quantity of x plus 2 plus the log base 6 of the quantity of x minus 3 is equal to 1. On the left-hand side, we have these two logarithmic terms, or logarithmic expressions, that are being added. There's a property of logarithms that says that becomes a product inside of a log. And so I'm going to write this down as the log base 6 of x plus 2 times x minus 3 is equal to 1, which the right-hand side is unaffected. Now, inside the log, x plus 2 times x minus 3, I can multiply. And so we have the log base 6 of x squared minus x minus 6. That's from foiling, is equal to 1. Now I want to convert this into an exponential equation. And when I do so, I think, what's the base? And the exponent is 1. So this becomes 6 to the first power is equal to x squared minus x minus 6. Subtracting 6 from both sides to end up with 0, I am going to end up with x squared minus x minus 12 is equal to 0, which I wanted to do because, I don't know if you noticed this turned into a quadratic equation where we had an x squared, which is most easily handled in this case by factoring. So x squared minus x minus 12 factors into x minus 4 times x plus 3. So we now have x minus 4 times x plus 3 is equal to 0. So from this equation I have that x is equal to 4 or negative 3. But wait a minute. I don't know if you remember, but a log has to hold a positive number. And so it's safest for me at this point to put 4 in place of x and then negative 3 in place of x in each of these logarithmic arguments to see if anything goes negative. And what I'm going to find out is if I put negative 3 in place of x, actually for either one of these, the argument goes negative. So negative 3 is not actually a solution. Here's the deal. When you solve a logarithmic equation, you've got to make sure that you don't have a 0 or a negative inside of the argument of the log. Here our answer is simply x is equal to 4. Referring back to the instructions, give exact answers and approximate answers where applicable. X equals 4 is a beautiful answer. Leave it alone and walk away. Next, 3 times 4 to the x minus 5 is equal to 10. We're mixing it up. Is it exponential? Is it logarithmic? Yeah, you need to be able to recognize these by looking at them. This particular equation is an exponential equation because we have a variable in an exponent. Guess what kind of equation it would be if we had a variable in a log? Haha. What we want to do is we want to isolate first the term that has the exponential factor, and then we want to isolate the exponential factor itself. So let's see how that goes. To isolate the term 3 times 4 to the x, I need to add 5. So adding 5 to both sides is going to give me 3 times 4 to the x is equal to 15. Now I want to isolate the 4 to the x. Since it's being multiplied by 3, I'm going to divide 3. By the way, 3 times 4 to the x is not the same thing as 12 to the x because there aren't parentheses around the 3 times 4. The base is only what the exponent is directly touching, okay? Now that we've gotten through that, if we divide both sides by 3, then we end up with 4 to the x is equal to 5. It's just like the first problem. So what we're going to do is we're going to apply the natural log to both sides. natural log of 4 to the x is equal to the natural log of 5. And then use that property of logarithms that says that I can bring an exponent out front. By doing so, we obtain x times the natural log of 4 is equal to the natural log of 5. And then we're going to divide both sides by the natural log of 4 to ultimately isolate x. And so x is equal to natural log of 5 divided by the natural log of 4, which my calculator tells me is approximately 1.1610. Exact answer, approximation accurate to 4 decimal places. Moving on. Back to a logarithmic equation. Same instructions as they are throughout this entire video. Log base 2 of x plus 5 plus log base 2 of x plus 4 is equal to the log base 2 of 2. We need to combine logs first. Whenever you've got more than one log in an equation, actually when you have more than one log on one side of an equation, it's a good idea to combine those logs. Because these log terms are separated by a plus sign, we're going to combine them through that property that says we now multiply the arguments. What that's going to look like is log base 2 of x plus 5 times x plus 4 is equal to log base 2 of 2. So if we like, we can simplify. We can end up with log base 2 of x squared plus 9x plus 20 is equal to the log base 2 of 2. And before you start getting all carried away, check this out. On both sides, the bases are the same, base 2. And so the arguments are the same. We can just strip away the logs entirely. And when we do, we end up with x squared plus 9x plus 20 is equal to 2. Okay, that may have been a little bit weird. Look, if the exponents are the same and the bases are the same, then the results have to be the same, right? Okay, another way to look at it. After combining the logs on the left-hand side, we have log equals log, right? Okay, what's the base? 2. So make both sides the exponent on 2, and then the cancellation property kicks in because the bases now match. No matter how you slice it, we have x squared plus 9x plus 20 is equal to 2. That is a quadratic, and so I'm going to get everything on the same side. X squared plus 9x plus 18 is equal to 0. That's going to factor into x plus 6 times x plus 3 is equal to 0. And that gives me that x is equal to -3 or -6. I need to make sure that this doesn't cause any problems because this was a log equation, right? If I put -3 in place of x for x plus 5 and then for x plus 4, we have no problems at all. So -3 is good. If I put -6 in place of x for x plus 5, that goes negative. That bumps -6 out of the running. And so the answer is simply x equals -3. Remember, you got to double check when you started out with a logarithmic equation. Next, we have 450 times 3.02 to the 3x is equal to 180 times 5.68 to the x. Okay, this one looks like it's going to be a challenge, and there are actually a few ways that I can think about going about doing this. I'm going to show you what I think is maybe the path of least resistance. What I'm going to do, we have this 450 out front of one exponential factor, and then we have 180 out in front of the other exponential factor. It'd be easier for me if we got rid of one of those. So what I'm going to do is I'm going to divide both sides by 180. The reason I'm picking 180 is because it's the smaller of the two numbers. Nothing more interesting than that. On the right-hand side, the 180 divides out. On the left-hand side, well, the zeros divide out. We have 45 over 18. Dividing out the 9s gives me 5 halves. So we have 5 halves times 3.02 to the 3x is equal to 5.68 to the x. Now I'm not going to try to get too clever here. I'm just going to say, look, we have variables in exponents. When that's the case, I want to apply logs to both sides. I'm going to use the natural log. And so I have the natural log of 5 halves times 3.02 to the 3x is equal to the natural log of 5.68 to the x. The one where the exponent is 3x, that 3x as an exponent does not apply to the 5 halves. So I do not get to pull this out front yet. Don't do it. First, what I'm going to do is recognize that I have a product inside of a logarithm. And so I'm going to split those up into a sum. So I have the natural log of 5 halves plus the natural log of 3.02 to the 3x is equal to the natural log of 5.68 to the x. Now the 3x can come out in front of just that term, and then the x can come out in front of the term on the right-hand side. We end up with the natural log of 5 halves plus 3x times the natural log of 3.02 is equal to x times the natural log of 5.68. Now what we have is, believe it or not, this is a linear equation. The reason I can say that is because nothing interesting is going on with x. It's not wrapped up in an exponent. It's not inside of a logarithm. In fact, the 5.68 log, it's just a number. It's just a number. As such, what I want to do is get the x's on the same side. As before, I'm going to do so by subtracting. And so in this case, I'm going to subtract 3x times the natural log of 3.02 from both sides. Because I don't have like terms on the right-hand side, while on the left-hand side, that log term goes away, and I have natural log of 5 halves. On the right-hand side, I have to write them as separate terms. X times the natural log of 5.68 minus 3x times the natural log of 3.02. You notice I put the 5.68 and the 3.02 in parentheses. That's partially because when we started the problem, they were in parentheses. At this point, it's also to make sure that everybody knows that for the first argument, the 5.68 is the whole argument for the log. That is to say, it's not the natural log of 5.68 minus 3x, something like that. It's just to make clear everything to everybody what's going on. Hey, I have x's in both terms on the right-hand side. I bet we can factor and then divide. So when we pull the x's out of those terms, we end up with natural log of 5 halves is equal to x times the quantity of the natural log of 5.68 minus 3 times the natural log of 3.02. Now I can divide both sides by that quantity in brackets. It divides out on the right-hand side. And I'm going to flip this around and write down that x is equal to the natural log of 5 halves divided by the natural log of 5.68 minus 3 times the natural log of 3.02. I agree it's not pretty. It's not about pretty. Anyway, my calculator gives me an approximate answer of negative 0.5804. If you're having trouble getting these answers out of your calculator, in this particular case, your calculator would need to know that 5 halves is the argument of the numerator's logarithm, right? So it's natural log of 5 halves. You would need to put the 5 halves in parentheses in your calculator. For the denominator, you have more than one term. So your calculator needs to know that that whole denominator is the denominator. So it should be in parentheses as well. Anything else for the calculator? Ask me individually. Here's the exact and approximate answers that were asked for. Okay, so at this point, if you're in, say, intermediate algebra or college algebra, you can be done watching the video if you like. The next two are more advanced, therefore pre-calculus courses. Here we have e to the 4x plus 4e to the 2x minus 21 is equal to 0. And this might throw us for a loop because you can't combine the exponential terms or anything like that. What we actually have to do is recognize that this is quadratic in form. You see, the first exponent is exactly double the second exponent. Therefore, we're going to factor this into a product of binomials. E to the 4x could be expressed as e to the 2x squared. That's what makes this quadratic in form. Once we recognize that, we realize that what we're really after are factors of negative 21 that add up to 4. And so e to the 2x goes inside of the parentheses where an x would go in the factoring. As far as that negative 21, how about a plus 7 and a minus 3? What this gives me is e to the 2x squared, that's e to the 4x, plus 7e to the 2x minus 3e to the 2x, plus 7 and minus 3 make plus 4. Negative 3 times 7 is equal to 21. And so that's just to justify that our factoring worked. And it's kind of a trick that you use when you see an equation in this form. Now, we have that e to the 2x minus 3 is equal to 0. Or e to the 2x plus 7 is equal to 0. Let's concentrate on that second one for a moment. This would mean that e to the 2x is equal to negative 7, but that can't happen because exponentials never equal negatives, right? It's not in the range of an exponential function. Back to the first one. Isolating the e gives me e to the 2x is equal to 3. Now, because the base is e, I can use a natural log. And so we have, if I just kind of squeeze it in, the natural log of both sides here. On the left-hand side, we can use the cancellation property. And we have that 2x is equal to the natural log of 3. And so x is equal to the natural log of 3 cut in half, right? Divided by 2. Which my calculator tells me is approximately 0.5493. Okay, so this one's a exercise in recognizing quadratic in form. As is our last example for this video, 2 to the 2x plus 2 to the x plus 2 minus 12 is equal to 0. At first, you're going to look at this and say, foul. 2x is not exactly double x plus 2. You're absolutely right. What we need to do is recognize that 2 to the x plus 2 represents a product in and of itself. This equation can be rewritten as 2 to the 2x plus 2 to the x times 2 to the 2 minus 12 is equal to 0, right? When you're adding exponents, you're multiplying, results, right? This now gets rewritten as 2 to the 2x plus 4 times 2 to the x minus 12 is equal to 0, right? So I turned 2 squared into a 4. And on that note, now 4 is a factor of the second term. Here's what I want to point out. It looks like 2 is a factor of all the terms. It looked like that to begin with. It's not. For the first term, 2 is the base of the exponential expression. For the second term, we now have 4 as a factor, but that 2 to the x was still the base of an exponential expression. Negative 12 is a factor of 2, but it's moot because the first two terms, at first, didn't have factors of 2. They had bases of 2. So I wouldn't be able to do anything silly like divide out 2's everywhere because they aren't factors. Okay, now let me clean this up and back to where we were. And now this is quadratic in form because the first exponent is exactly double the second exponent. So when I factor this into a pair of binomials, in the parentheses where I would normally be putting x, I'm going to put 2x. And now I need factors of negative 12 that add up to 4. How about a positive 6 and a negative 2? The first factor gives me that 2 to the x plus 6 is equal to 0. So 2 to the x is equal to negative 6, and I say no, it's not, because an exponential with a positive base won't give me a negative result. The other factor gives me that 2 to the x minus 2 is equal to 0, and that's perfectly possible. In fact, that gives me that 2 to the x is equal to 2. Since 2 could be rewritten as 2 to the first power, this one gives me that x is equal to 1.